delighted in the second head of the double bill to introduce Professor Robin Purshouse. Robin is a Professor of Decision Sciences at the University of Sheffield. I first came across Robin's work in the area of multi and many objective optimization. However, he had a very varied career and work in industry as well as academia, and he's also principal architect, I believe, of the Sheffield alcohol policy model, and also for sort of impacts into areas beyond engineering and computer science. Held a Future Leaders Grant from ESRC about a decade ago.
Thank you, Jonathan. And thank you everybody for inviting me here. So I'm going to, from the sublime to the ridiculous, perhaps, Aman, I'm going to talk about an application of multi-objective optimization, but applied to agent-based modelling in the social sciences. This picture that you can see is the Cascade Mountains on the west coast of North America, and the reason for that is that the findings I will show you belong to something called the Cascade Project, and that was combined analysis, I forgot what it's called now, combined analysis of agent simulations for drinking etiologies. And it involved the University of Sheffield, the Alcohol Research Group in California, the Centre for Addiction and Mental Health in Toronto, and New York University in New York City. And a lot of the products that we created from this you can find here at this Bitbucket. So a lot of it's been made open source. Should you be interested in any of what I'm about to show you. Okay. It's gone to sleep. There we go. Okay. So over the next half hour, I'm going to kind of give you a very brief introduction to what's called generative social science, and what that means, and inverse generative social science. I'll show you a particular target phenomenon that we're going to try and explain, which is alcohol use behaviours in the US. And explanation is quite important here. So a lot of the modelling is done for purposes of explanation rather than prediction. And so we have models that are relatively straightforward to understand, and they typically are based on theory. Here we're going to look at psychosocial theory, and I'll give you a brief tour of some of the theory we've been using. And then I'll show you how we've been using that within a multi-objective grammar-based genetic programming approach to solve these inverse problems before I conclude. So what's generative social science? So this is quite a famous quote within computational social science by Joshua Epstein, who says, if you didn't grow it, you didn't explain it. Okay, now this is in the context of agent-based modelling, where you define micro entities, and those are bound together by some mechanisms, and they produce an emergent macro phenomenon. And the statement here is that if those macro entities and those mechanisms didn't produce the target phenomenon, then you haven't got an explanation, or really a candidate explanation. So really we're talking about necessary but not sufficient conditions for explanation. And if I show you the classic, this is the classic agent-based modelling example, the canonical agent-based model. This is Thomas Schelling's work from the 1970s. So here you've got the macro entities, these agents, and here they have some kind of difference between them. So in this case we have some circles. These represent one type of agent, and we have these hashes that represent the other type of agent, and they have encoded within them rules around the preferences that they have for other agents who are similar to themselves in their neighbourhood. So they're on this checkerboard arrangement here, and if they're not satisfied with the proportion of agents who are similar to them, then they can move elsewhere. And what Schelling showed was that for very small tolerances for dissimilarity, you got this kind of emergent phenomenon. So you got this clustering of groups of the same agent together, a segregation effect. And so there was a claim here that in some way this micro level specification was saying something important about segregation. And here we're seeing it, aren't we? As kind of, we're not, as modelers, we're seeing the clusters, So it's kind of a qualitative representation of emergence, but that could also be quantitative. So we could try and measure this segregation using the segregation index. So this is the type of modelling arena that we're working in. And there are two kind of perennial problems with this type of approach. So the first is kind of problems to do with accepting explanations. So this is a quote from some skeptics of agent-based modelling in the social sciences. So they're saying the model is capable of reproducing a pattern of data, but reproduction is not explanation. We're in the territory of the fallacy of affirming the consequence. So just because something shows that it can reproduce the target, we shouldn't say that it is an explanation. And to be honest, very few people who work in agent-based modelling would ever make that kind of claim, at least explicitly. But then again, they might then use those models to make certain claims about reality or to look at certain policy effects. And there's kind of an implicit claim there that this is in some way representative. Okay. So we've got problems to do with accepting explanations. But it turns out we've also got problems to do with rejecting explanations. This is quite an interesting study from a few years ago. So they were looking at particular implementations of a psychosocial theory called the theory of planned behaviour. Now, a lot of psychosocial theories are not particularly formalised, so there has to be a sort of formalisation step that you go through in order to realise them within a computer simulation. And what these authors showed was that they showed 3 different realisations of one theory, and they showed that those different realisations could produce both quantitatively and qualitatively different emergent outcomes. So this is a problem now, because how can we reject the theory of planned behaviour in this application if some realisations of the theory of planned behaviour seem to be working okay, but some we're immediately falsifying? What does it actually say about the underpinning psychosocial mechanisms? So we've kind of got problems both with accepting explanations and, unfortunately, with rejecting explanations. And really this has seen a kind of turn towards inverse generative social science, which is looking at it as an inverse modelling problem. So rather than specifying our agents and running it and seeing if they could reproduce an emergent phenomenon, start the other way round. So define the target phenomenon to be explained, then search through the massive space, potentially infinite space of possible agent-based modelling structures to identify sets of models that can reproduce that target, and then look for what are the commonalities within those models that have been identified. Okay, so this is the general idea of inverse generative social science. It's an idea that's not particularly been around for very long, so this is a sort of nascent topic within computational social science. We introduced it at Gecko 4 years ago, and Joshua Epstein, who's one of the collaborators on this grant, wrote a sort of manifesto piece for this in the Journal of Artificial Societies and Social Simulation just this year. But there's a heck of a lot of devil in the detail of this, particularly point 2. So how you define a space of possible agent-based modelling structures and operationalise that is not a trivial matter. Okay, but you can see that there's the potential for computational intelligence approaches here, and my background is in computational intelligence, so this is the kind of problem that I like. Also in this kind of point 3, in terms of once we've identified these candidate models, looking for what's similar in them. From a theory building perspective, you might be thinking about sort of family resemblances between different types of theory. And again, clearly there's kind of a role for machine learning within identification of that. And there is already some work ongoing in that space as well. Okay. So this is the overall idea. I'm going to take you through a specific case study. This is the case study that we're looking at. So this is the dynamics of alcohol use in New York State, in the US, over time from 1985 up until about 2015. For men, it's in red. This is grams of ethanol per day on average for men in red, and for women in blue. And this is survey-based data, so there's some sampling error which is represented by the grey. Now, there's also biases in these surveys, so this is not the only source of uncertainty that's in this data set, but it's one of them. And what we see here is that there's quite this big trend during the late 1980s, early 1990s. We see a big reduction in male consumption, and then it kind of goes back up a little bit towards the year 2000, and then it's kind of levelled off. In women, it's a much gentler trend down, and then a more gentle trend going up as well. And For a time, it was thought that there was going to be some kind of convergence of these trajectories, but they have yet to converge. If we look at the data through to about 2021, which is the latest we've got, these trajectories have still not converged. Okay. So this is the thing that we're interested in explaining. The way that we're going to do it is by using agent-based modelling, and we're going to base it on psychosocial theory. There's 3 theories in play here, and these are theories that are already suggested and used within the alcohol research community. So the first is dual process theory. So this is where we combine reasoned action, so sort of intentional behaviours, with habitual behaviours. So we think that people sometimes behave intentionally, they sometimes behave habitually, and what we actually do in reality is some kind of mix of that. The social norm theory, which says that there's kind of societal norms for how people do behave, how they do drink in this case, and also norms around how people should do things, so perceptions of what people should do, and that they impact on individuals' behaviour. And then we have social contagion theory, which is the more micro-level version of that, which is where personal networks are creating influence effects, or selection and influence effects within networks. So as part of this project, we developed agent-based models of all of these things, and we had different people working on different models. Now, in order for all of this to actually be integratable together, we had to create our own software architecture, so that at the end of the day, we'd end up with components we could work with. I'm not really going to talk about that today because there isn't time, but that's a totally different talk, is kind of that software architecture for agent-based modelling, and we've made that publicly available, and we're now rolling that outside of alcohol into other health behaviours. So we have a smoking cessation model that we're developing with University College London, and we've also got a food choice behaviours model as well based on this architecture. So I'm going to give you kind of a conceptual rundown to these psychosocial mechanisms, and then I'll show you just a few of the equations that are involved. So all of this gets formalised, but some of it I'm going to have to show you in order that you kind of appreciate what will happen with the genetic programming. But conceptually, I'll go through everything. So we've got an intentional pathway over here, and this is feeding into the idea that people have attitudes, they have perceived norms, and they have perceived behavioural controls that affect their intention to perform a behaviour. And that they also have some level of autonomy that determines the extent to which they just do what they like, as opposed to doing what they think perceived norms are. And all of this in the end is going to go into some sort of what we call a schema selection, which is categories of behaviour. So if we're to do with drinking, we're going to define this as drinking on any particular day. And we might abstain, so we don't drink any alcohol on that day. We might drink a small amount, we might drink absolutely loads, okay? And these things define certain schemas of behaviour. And then once a schema is selected, there's actually the performance of that schema. So we might go in thinking we're not going to drink anything, but then actually we do drink something, okay? So there's kind of a difference between the intention and the actual behaviour that gets performed. So that's on the intentional side. This is dual process, so what's going on the other side is a habitual pathway. We've got habits that are formed by behaviours that are repeated over time. The way that we kind of operationalise this is through the idea of like a habit bag. So the agent has got a bag with all of the things they've done over the last N days. And if we're following the habitual pathway, we stick our hands into the bag without replacement and we pull that one out. Okay, and we perform that behaviour if it's habitual. If it's intentional, then the behaviour is performed and then that will go into the bag when it gets replenished. So we kind of have both habitual and intentional behaviour. Another thing that's important is there's the norm theory. So I said there's kind of norms around, descriptive norms around what we perceive people do, and injunctive norms around what we perceive people think we ought to do. Okay, and those things come together to form societal norms. Those things are perceived by agents, but there's in the alcohol community, there's known to be some perception bias here. People think they drink more like other people think. They think other people drink like they do, rather than how other people actually drink. Okay, so there's some kind of perception bias there affecting it as well. Okay, and then this goes into that dual process theory. So perceived norms was one of the components that you saw previously. The other bit that we've finished, but you won't actually see today, is the social contagion theory. So these are agent-based models, so we've got social networks as well embedded in this. And here we've got behaviour based on average drinking of close contacts, also influencing perceived norms. So we can have perceived norms coming from a sort of social network, and we can have perceived norms coming from a more cultural, societal perspective. Okay, so that's conceptually what's going on, and then I'm going to show you a little bit, just enough of the formalism to get by. So the first thing to be aware of is that what's going on inside the agent's head is operationalized as a multinomial logistic regression. The agent's behaviour, that drinking schema, is Y. I here represents the ith agent, so that's the individual, and J is the particular schema they've performed. Okay. And then over here, we've got basically a regression kind of equation. So we've got some attitudes that relate to a specific agent for a particular type of behaviour, and we've got some norms, and these things are weighted together. Okay, so fairly standard sort of representation, familiar to people who do logistic regression modelling. The attitudes in that equation there are fed by some inherent desire that this agent has to drink in certain ways, and that's weighted by their autonomy, which is how much they ignore social norms. And similarly, their norms have the kind of inverse of that weighting, and they're formed from these two things. At the moment, it's an additive sum of the log odds of those injunctive norms, and again, they relate to specific drinking schema, and the I is in brackets because here the agent is perceiving a reference group. Okay, so they're perceiving people like them, and that themness is according to other attributes of the agent, like their gender and their age group and their ethnicity. So this is probably about enough to get by with what I'll show you next. Okay. So what we then do is turn that into a grammar. I'm going to introduce that slowly. So this is the highest bit of the grammar. So the first thing that you'll see is that we're going to retain the log odds representation. So we're not going to throw that away, so we're going to operate within that. And what we're really going to do here is build a kind of symbolic regression inside the agent's head. Okay, so we're going to have a log odds intention is some expression, and these models have a lot of parameters associated with them, so it turns out we're going to have to select some numbers as well for these agents. What happens next is we look at what happens inside the log odds intention. So we can have a variable or a constant times the log is enforced, and then inside there we've got some odds. Okay, and we'll define those in a moment. And over here on the far right, we're allowed to add two log odds together, which is pretty much the only thing that we can do with log odds that's allowed in a log odds representation. So it's a little bit boring, really. And then with the odds, we can do a lot more now. So in the odds representation, here are some simplified expressions of things that will behave themselves when we consider them as odds. So we've got this inherent desire of the agent, we've got their perceptions of descriptive and injunctive norms, we can add things together, we can multiply things by a variable or a constant, we can square root things, and we can square things. So there's more operators that are allowed at this point, and we're allowed to select from these. And then there's a whole load of variables and constants that we can select from, and the most important one is this one, which is the autonomy of the agent. So here agents have autonomy that's heterogeneous between agents, it's defined according to a distribution, and this is probably the most important thing that's in here. And there's various other things. There's an attempt to do parameter optimization in here, so that you can see you can define a variable to 2 decimal places by selecting integers from this representation. And then we got some parameters. Now here we can choose from 3 sets, so we can choose a few parameters here, but then we can also, this is quite a big model, so it goes beyond the logistic regression. There's a lot of other things going on. And we can choose ones that will do, that we fitted to male drinking, ones that we fitted to female drinking, and ones that we've tried to fit to both at the same time. And one of the issues with that model that I was showing you is that it doesn't do a very good job of fitting men and women at the same time. So it's this psychosocial theory is supposed to be a universal theory. It's supposed to explain away things like gender differences in drinking. And it doesn't actually do a very good job of that. And you know that it needs to, because we saw that the male drinking is dropping very fast, and the female drinking is following a much shallower trend. Okay, which is one of the motivations for trying to do this. The evaluation functions that we're using here, we take ones from approximate Bayesian computation. So if anyone's familiar with that, this is a typical implausibility metric. On the numerator, we're looking at we run the simulation, we get the outputs for different targets at different points in time, we compare them to the actual target data, we take the absolute difference on the top, we average it across a number of replications, so the n here are different random number seeds, so the run is conditional on the random number seed, and then we take the maximum across all of the targets, okay, so that the maximum implausibility, the worst case that we see across all time points for men, and then we also do it for women separately because we're interested in looking at whether or not there's some kind of trade-off here in the modelling. And then finally, for our third objective, we're counting the complexity of the model itself. How much have we stuffed into that logistic regression? Okay, the framework I'm not actually going to say much about, but it's kind of a conventional multi-objective grammar-based genetic programming framework. This is one that's already been published. It's something called Pony GE2. It's a Python toolbox. It uses NSGA2, so a very conventional multi-objective optimizer for the selection mechanisms. It's using subtree crossover and mutation for the variation operators. The budget, as with a lot of genetic programming applications, is quite large. So it's 250,000 evaluations altogether. We split that into a population of 500. Again, not unusual to have large populations. Not so many generations, and we have 10 replications because there's quite a lot of stochasticity within this model. And it takes us about a week. So we run these things on a workstation, quite a fast workstation, but it's taken us about a week to get these results. So we don't do any benchmarking actually yet because we just don't have the resources to do it. So it's a lot of time and it's also a lot of energy that's being used there. In terms of the results then, so I was fortunate that Hemant already did all the multi-objective introductions, so thanks for that. So what we're seeing here is a trade-off surface. We have the three objectives. The third one here is represented by the colour of these different solutions. So red is a very highly complex rule. Light blue is something that is a very low complexity. The male implausibility is shown here, and we're trying to move this way. The female implausibility is here, and we're trying to move this way. So ideally, we want to be down here. These are models that are showing good explanatory power. Okay, and what do we see? We see that we've kind of got a trade-off surface of low complexity models kind of sitting over here, and that if we want to improve it this way, we have to pay a bit of price of additional complexity. So we've got kind of darker blues here. If we want to get the very best female implausibilities, you'll see that it's kind of dark red, but to get those, it's very, very marginal, that performance advantage. Things are a little bit different with the male implausibilities in that we see this big disconnection. So to get the very best male implausibilities down here, we have to pay a cost. These things are very, very complex expressions, but it's also quite steep. And for this reason, we decided to focus on this one here in this so-called knee region as potential solution of interest. So this is something that's been constructed by the genetic program, and we call this the alternative structure. These ones here are the originals fitted to just the male data, to the female data, and the balanced one as well. So they're kind of in the mix. Okay, so the genetic program hasn't fundamentally outperformed the original versions. They're still there, kind of in the mix. So this is on the calibration window, which is most of the data set. We then run it again on the validation window, and fortunately the alternative model is still there, kind of in this area of the front, so this is good news. A lot of the stuff has been kind of pushed together. We see now that the ones here that were giving us the best results for females that were highly complex are just in the mix, so an indication that was overfitting. Interestingly, now I would have thought that these reds would also have pushed more this way. In fact, they haven't, which is quite interesting. So they still retain their competitive advantage, but they're still very, very poor at fitting to the female time series. We can see that here. So these are the these are the time series for the selected models. So the first three were that original model, that's just had its parameters calibrated. The alternative model was that square that we saw, and then we've got the minimum and maximum complexity. Here, reds is male, blues is female, and the target data is the lighter colour. So over here, this is the maximum complexity, and here you see the sort of catastrophe on the female fit. So this is what it's trying to fit, this light blue thing here, and that's what it actually did. So it's pretty poor. But it fits quite well to the male time series, and the confidence interval around the prevalence of drinking is quite tight. So if you depart from getting the right number of drinkers as opposed to abstainers in your model, you pay quite a big penalty for that. Whereas you can see that the confidence intervals here are a bit larger on things like drinking quantity and drinking frequency. So this is the time series data. Again, this is the dividing line between the training set and the test set here. I'm just going to show you some results from this. So firstly, this is the minimum complexity model. So it just says that the log odds intention is a weight times the log odds of desire. And the desire is some inherent disposition that the agent has to drink, and it's predetermined for each agent. And it doesn't really change over time. So it's basically saying that it's a constant. It's going to fit something that looks a lot like a straight line. That's the simplest thing that it can do. And the parameter selection can be male if you want that straight line to fit well for males. And it turns out if you choose the female parameter selection, you get a line that fits quite well for females. I'm not going to dwell much on this, but that's the maximum complexity structure. So these are the sort of structures that do particularly well on either the male or the female targets. And we saw definitely in the case of the female targets that this is overfitting. Okay, so it's pushing in more structure, but it's using it just to try and get a little bit of extra parameter performance in effect. And then the alternative, that square structure, is this one here. This is quite an interesting structure because it has a sort of family resemblance to the original when we looked at those equations. And it involves quite a lot of the concepts from the theory. So it involves injunctive norms, how the agent perceives other people think it should behave. It involves the descriptive norms as well. It involves the agent's inherent interest in drinking. It involves the extent to which they prefer their own interests over their perceptions of norms. It also, this one uses the balanced parameter set as well, rather than the male or the female. It all looks pretty good, except for this little cheeky fellow here, this minus sign. So there's a minus sign on this term, which is beta attitude times 1 minus autonomy, log odds of beta norms, square, and the important thing is this bit, square root descriptive. So it's saying that kind of a more extreme version, this kind of creates a more extreme effect of the descriptive norms, is going to drive the agent's behaviour, but it's going to drive it in a negative way. So it's reducing the overall log odds, which is kind of like the agent saying, okay, I see how people behave, and I'm not going to behave like that. I mean, you might argue that's okay. Maybe that is what people do. But it's questionable, I think. So people who are domain experts in social psychology would question that this would be reducing the log odds. Okay, so we found something that is able to resolve a bit of the trade-off that we saw between male and female drinking, but we've got a potential issue with meaningfulness. Just want to show you the convergence plot. So again, we've got convergence measured in terms of hypervolume here. So just to show you this thing is converging. The other thing that we did here was at these kind of junctions where we saw big improvements in performance, we looked at what structures were actually in the population of the genetic program at that point. And we're tracking terms that appear in that final compromise design. And we find that actually we found the structure kind of about midway through. And what's happening over there, that very shallow gradient, is it just tuning the parameters slowly of that structure. So it's trying to improve the parameter fit to the particular structure. in terms of kind of where this ends, so yeah, as I say, this particular case study, so we found something that could fit the male and female targets. It did use the underlying psychosocial theory, but its meaningfulness is questionable. And we published this this year. Definitely it is the case that not everything that the machine fits is meaningful. And in a previous study, this was a study that used social role theory to explain similar trends. And of everything that was produced, so we produced quite a lot of stuff on the actual Pareto front, we only in the end found 3 candidate solutions that had theoretical meaning. And we involved a social psychologist from Toronto kind of in the loop on the genetic programming process. And what we found is that we had to vary the grammar. So we had to change the constraints encoded in the grammar to try and help the genetic program to find things that were more theoretically meaningful. And we went through 3 iterations of that process. And in that paper, we published what the 3 grammars look like. So you can sort of see the evolution of the grammars. And in the end, we did find things that were meaningful. Just like Hemant's problems, these are very computationally expensive. So we need efficient inference methods. You might look at our sort of approach to training and testing and model selection and think, oh my God. But it's not easy to do this. But it needs better inference methods. Surrogate models, clearly there's potential use of surrogate models within this space, but we're talking about, because it's genetic programming, we're talking about structural space differences. So somehow we have to define meaningful distance metrics within a structure space. And I'm very, if anyone wants to help or talk to me about that, I'm very interested in how we do that. And also, there's clearly a case here for bi-level structure parameter optimization. So can we predict what the results of a parameter optimization might be for a given structure, for example? So there's kind of a fit here to bi-level optimization. The other thing that's important here is that not just that we get kind of diversity across that Pareto front in the sort of performance space, but what's actually important here for theory building, if we think about trying to generate candidate explanations and trying to develop a family of those, is that we need also potentially diversity preservation operators in the decision space as well, probably at the same time as in the objective space. This is something that we did, and probably I spoke about the last time I was at Exeter giving one of these seminars, where we were looking at niching operators in decision space to find very different parameterizations of an agent-based model with a given structure that would give you different options for parameterizations. So that's kind of it really. So yeah, it was a big team effort. This project finally finished. It was a 6-year project, National Institutes of Health in the US, and altogether there were 20 of us involved in that. So I want to acknowledge everyone over those years for all of the work that they did. And thank you very much. Happy to take questions. Yep.
I'm just wondering, why did you need to fit the male and the female at the same model? Why didn't we try and create a model for the female and a model for the male and compare between them?
Yeah. So you mean structurally?
Yeah. So yeah, running it as just one for the female and one for the male.
Yeah. So you could. So you could do that alternatively. So. But part of many of the reasons for these kind of theories, so in the social sciences there's kind of 2 types of approach. There's kind of what they call a determinants approach, where you would have a classical statistical approach and you would put in variables like gender and age group and ethnicity and socioeconomic status, and that these things are known to be predictors of certain behaviours or outcomes for people. But they're not really mechanism-based. So the idea is to kind of replace that determinants-based approach with something that's more explanatory, that says why gender is important, or why do we see patterning by gender, why do we see patterning by age groups. That's not just about that as an identifier. Yeah. So now, and most psychosocial theory assumes the same explanatory structure, regardless of what humans were talking about. Okay. So regardless of whether we identify as a man or a woman, regardless of what age group we belong to, we're following the same cognitive template. So and so there's probably, if you say, well, actually, I found a structure for men and a structure for women, you can say that, but it would question a lot of the sort of fundamental basis for sort of psychosocial theorising. The area that maybe, and there's probably, I don't think many people think there's a lot of justification for building different cognitive models for men and women. There is, where I have seen talk is about sort of neurodiversity and whether or not people who are autistic might have a different cognitive model to people who are not. So that kind of thing, maybe you would have more traction with saying that you've got different cognitive structures, but it's not easy to go to social psychologists and say, no, actually, I think there's fundamentally different cognitive models at work here. So that was a long answer to your question.
Yeah, I understand where it's coming from, but what I'm wondering is, wouldn't it not been interesting to see how these different models would actually, how different they would be, because it might not that they are so different, but...
Well, we do see it. So when you do the trade-off, yeah. So here, so every one of these is a different model structure. It's just that we happen to have evaluated it for both male and female target data. So these red models here are the ones that these are ones that are good for representing the male cognitive program, and these are the ones that are good for the females. And they are different models, so we still end up considering a whole family of models, and some of them work better for men and some for women. Yes, Richard.
Thanks, Alex. It's really interesting. I'll think about it over a drink this evening. But is the well, lots of questions. Are all of the points on your Pareto front, are they structurally different, or are neighbours just slightly different calibrations of the same?
Yeah, some of them are. So because we allow some element of parameterization is encoded within the grammar. Yes, some of these will be similar structures but slightly different numerical encodings. Yeah.
So in a similar way, I mean, your grammar could have, but didn't include only, or a constraint to only have a positive coefficient for your beta attitudes term. And I wondered whether you had done an ablation study. You know, have you just wiped out that term and made the coefficient 0, or because the same coefficient occurred, I think, in the model that you showed us later on. So I wondered whether that was just an inflexibility in your model.
Yeah.
Sort of force that on you.
No, that's a good point, and we didn't. There was no screening study done before this, and it probably would have benefited from that. Yeah. Yes.
So you've based all of this on, psychosocial theory and things. An obvious extension for me to think about is, could you have sort of in statistical modelling, done like a nugget term which sort of just absorbs some stuff. So have you looked at adding a couple of just extra variables that are not related to any kind of theory, and see if you calibrate these specific variables, or try and add a few extra nonsense equations? Can you actually explain it really well? Yeah. And then could you go back to the psychosocial people and go, this is what you're missing. Can you look at trying to explain this?
Yeah, I mean that's a good. We haven't done that, and you do see that kind of thing appearing in some models. I can think of a particular model that's got this
Sort of
almost arbitrary function. It's a disease progression model where a lot of it is based on knowledge about physiological knowledge about disease progression. But there's a point where it has this arbitrary functional form that appears that they then essentially tune so that it fits the data. I don't think there's then any discussion of, okay, well, how does that relate to this pathway that you've described? But I mean, that's a natural thing to do with it. Yeah, I think that's a good idea. We haven't done that, no. Yes.
So I'm not sure if I captured the result, but can this model give us the answer, like for instance, the main difference between men and female consumption is towards the social norms, and you have more social norms acting in one way or the other? Is this something that we could use to answer that, and any of these models answer that?
Yes. So I think the answer is yes, but there are caveats. So we can. I haven't done it here, but we can look at what mechanisms are firing when. So, for example, I didn't describe the processes by which the norms are updated. So there's kind of a lot of feedback processes at work here. We can measure what's going on in those feedback processes. So you could look at the extent to which what those norms are looking like for males and females, and how each of them is updating over time. Okay, so what's happening in those feedback processes? So we can look at that. The reason why the caveat really is that with these models, with them being dynamical system models, we are trying to get them to run from a defined initial condition. So we operate these without burn-in, which is quite unusual within a lot of agent-based modelling. So with a lot of agent-based modelling that's particularly not that empirically related, is that you have a kind of general qualitative target phenomenon. You run the model from some random initial condition, you get this sort of burn-in behaviour, and then you get an emergence. And you're only interested in the emergence, okay, not the transient that led to it. But here, this is quite a bit more challenging, because we're saying, all right, this is like a proper state space model, if you like. We're going to define an initial condition, and then we're going to define a set of equations, and if you've got that initial condition right, there shouldn't be any burning. This thing should just run, yeah. And that's what we're trying to do here. The potential weakness for its explanatory power is that you have to encode those initial conditions, obviously, with what the current situation is for men and women. So we've got measurements of what men and women's conditions are at baseline. And depending on how much dynamics is in here, those initial conditions could dominate the response. So you're baking in kind of what you don't want to bake in, which is this determinants-based approach. You're just baking in that there's differences at baseline between men and women, and with this you have to do it, because this is the dark ages, right, for alcohol data. This is as early as you can get. Most people would not be as insane as even to try starting here. They'll be starting like in the year 2000 or something. Yeah. So kind of trying to do any kind of long-run analysis is quite challenging. And clearly for something that's been around for a long time, like alcohol, and if you want to say it's about norms, then you have to think over quite long time scales. I haven't done it because the idea just depresses me too much, but COVID offered an incredible opportunity to look at norm formation, and I haven't seen any studies yet, but I'd love to see studies that have done that, because there you've just got a lot more data available to look at normative processes. So, but here we know that normative processes are going to be important, but they're playing out over significantly longer timescales. These are relatively stable systems. Stuff's very slowly changing within them in general. You need something major, like COVID. So alcohol will become more interesting once you get these 2020 plus bits of the time series. We know that some very big and quite disturbing changes in people's drinking that happened sort of post 2020. And big increases in liver disease mortality and big increases in opioid and alcohol co-use mortality as well in the US.
That's the last one, DC.
Thanks, Robin. Did you do any changes in your grammar to reduce the overfitting without compromising the performance, especially on the male side?
To try and stop the overfitting. Yeah, we did. So we had a much more constrained version of this grammar that was much more conservative, and that I personally preferred. So there was some debate within the team, and Joshua Epstein, who is the big agent-based modelling expert, he didn't want as many constraints. So he wanted to allow the genetic program to be more creative within the context of a log odds representation. But if you look at that really complex model, is that in any way producing a meaningful log odds? It might, but we had a version that imposed a lot more constraints on that to avoid the overfit, because you can get some very, very eccentric things going on within the log odds expression otherwise.
But that was not accepted or didn't go forward.
We did it. So we have result. I just haven't presented them. So yeah, there is another set of results that relate to a much more conservative grammar. Yeah.
I think I'll leave the questions there. If there are any further questions for Robin, we can have that over coffee and tea. And if we could thank Robin and Helen once more, please.